Do you know that 82% of Android devices were susceptible to at least one out of 25 vulnerabilities in the Android operating system? Do you know that the number of malicious apps fell to around 700,000 between January and June in 2022, a decrease of around 48%? Hello everybody, my name is Zakaria Al-Shara from Software Engineering Department at Jordan University of Science and Technology. Today I will present my paper NIV-Detector, an automated approach for detecting next intent security vulnerability in Android applications. First, in Android inter-process communication, any component can't start or communicate with any other public component that are belong to a different process or application in the same Android device, where the private component should be protected and only be accessible by the same process, not by another process. Android inter-process communication should preserve its component encapsulation and prevent any breach or break for this encapsulation. However, malicious apps can breach access and directly start private components from another process, which cause mixed intent vulnerability problem. The leading cause of NIV comes from launching unsafe intent or nested intent sent by the malicious application on the same Android device. The guideline of this presentation: first we will talk about the inter-process communication of the Android platform, then we will talk about the next intent vulnerabilities, then how we can detect these next intent vulnerabilities from the Android source code, and finally we will propose our tool or plugin an NIV-Detector, then the evaluation and result of our tool, and finally the leading cause of mixed intent vulnerabilities that are coming from launching unsafe intent that are sent by malicious applications. To better understand the inter-process communication for the Android platform, as we can see here, first, the client app create an intent for its client callback activities and add an extra to the intent that it will be used to start the provided app API service. After that, the service provider processing the requests that are coming from the client app and use the intent that the client app provided to start the client callback activity that are reside in the client app. However, the things to take note of here is that the provider app is calling start activity within its own app context, not from the client app context. This has two consequences, both of which are suboptimal. The first consequences, since client callback activity is being started by provided app, it must be marked as exported, which allows not only provider app to start it, but also any other app on the device. The second consequences, the nested intent passed to API service can be used to start any activity that is part of provider app. This includes private, maybe potential activity, or sensitive or non-exported activity. So, a malicious Android application can invoke the private component of a vulnerable Android application, which cause next intent vulnerability problem. The main problem or the main cause of an NIV that the vulnerable application are designed or developed in such a way to be unsafe to redirect component within an Android inter-process communication. NIV was firstly mentioned by Wang et al. Here is the scenario of the next intent vulnerability. We have an attacker app and vulnerable provider app. So to demonstrate, consider what would happen if the calling app didn't provide an intent of its own activity, for example, a client callback activity, but instead put an intent to start a private activity within the provider app. Because an instead intent is used, it's difficult for a provider app to guard against intents that target private, potentially sensitive activities. Because the provider app is calling start activity on the intent directly, it's able to start API sensitive activity even though it is not exported for the attacker or client application. To identify an NIV problem from the Android source code before it's released or upload to the store, because many related work are dealing with this problem after released time by making such or some kind of dynamic analysis to protect or to detect this problem. But in our paper or our tool are designed to detect the NIV problem from the code as a code smells during development time. So first we need to identify inspection button to detect the NIV code from the Android source code. This inspection pattern, it's rely on the structure and the syntax of NIV code scenarios, and then analyze these scenarios in order to extract these inspection patterns. And after that, we need to identify the inspection rules. We need to study the behavior or the semantic of the NIV code scenario and analyze this scenario in order to extract the inspection rules. Here we have two tables. On the on the left hand side, we have the possible method that can be used to detect a nested intent. And on the right hand side, we have the inspection button that are written in a regular expression. As we can see, we have around 6 scenarios that can be used to attach or detach the nested intent from the service provider or provider Android application. And each pair of this scenario, for example, the first and second method are designed in the first inspection pattern. The third and fourth one are designed for the second inspection pattern, and the fifth and sixth one are handled by the third inspection pattern. Sorry. So here we analyze the structure and syntax of the method in order to extract the inspection pattern. And we notice that, as I mentioned before, the first method pair has similar structure and syntax, the same as for the second and third pair, where the inspection pattern are represented as a regular expression using regex language to detach nested intent. For example, inspection pattern 1 represents the pattern for the first two methods. Variables are denoted between dollar signs that have some constraints denoted between square brackets. For example, the type of variable base must be android.content.intent. Another constraint related to the occurrences. For example, statements variable that represent any statement in the code could be occurred 0 or more times. Here we have after analysis, we have 4 inspection rules. The first rule, talking about the base intent. The base intent is the intent that attaches another intent, which make the nested intent. The base intent must be delivered from the outside, or for example from the client app, because the nested intent, if it is coming from the same Android problem, it will not cause any NIV problem. The second inspection rules, the nested intent must be attached to the base intent to make a nested intent. And the third rule, talking about it should be the nested intent should be injected as a parcel. A parcel, it's an object that could be parsable by Android platform, and it has many action to do. The original nested intent must be launched as an inspection rule number 4, because if we have such a kind of an nested intent and this nested intent is not launched, for example by calling start activity, it will not cause any NIV problem. Here is the architecture of our NIV detector architecture. As we can see here, we built our tool as a plugin over an Android Studio to facilitate for the Android developer to use it during development time. The main goal of the first component, which is an NIV parser, is to import Android project and extract the structures and semantic of their source code. Then 3 modules work together to link the text, structure, and behavior of the source code. In the first, the structure of source code is parse associated with its text. Then, parser builds the abstract syntax tree that defines the structure of the program. After the syntax AST nodes of each file, for example Java classes and XML file, are created internally by parser and are presented by AST node instances. The AST node have a direct mapping to text source code, for example Java classes and XML files. Then the behavior of source code is defined associated with its structure. A PSI tree, which is a program structure interface tree proposed by IntelliJ or Android Studio, is built on top of the AST tree. The PSI tree adds semantic and techniques for manipulating source code structures. Here a screenshot of our plugin. As we can see here, some kind of code that cause an NIV problem. And here, after using our plugin, an NIV solver, for example, here we can see how many problems we have. The problem will be highlighted by our plugin to denote for the developer that there an NIV problem in your source code. We evaluate our tools in 100 top-rated Android projects that are cloned from GitHub, and each project is imported into an Android Studio where an NIV-Detector, which is our tool, is installed. And during this evaluation, we will answer 2 research questions. The first research question: what is the accuracy of an NIV-Detector in terms of detecting NIV smells? And the second research question is about what are the NIV smells that cannot be detectable by an NIV detector. From 100 Android applications, we found 10 Android applications that have an NIV code smells, and here we show the result in terms of true positive, false positive, and false negative. Here the number of NIV that are inspected manually by an expertise developer of Android applications. For example, WordPress Android has 3 NIVs. Our tool can detect 2 of 3s, but 1 are not detectable. We will talk about this case later. And for other Android application, all NIVs are detectable by our tools. In this case, where, for example, in WordPress Android, there is one case that are not detectable by our tool because our tool is based on static analysis and some information are not available at build time, but we need to a dynamic analysis to get more information about these problems. So in the future, we are aiming to mix between static and dynamic analysis to grab or detect all NIV's smells in Android application. So as a conclusion and the future work, the malicious Android application can directly launch a private component from another, which cause breaking component encapsulation and an IV problem. There are many tools are proposed aiming to discover an IV after the application is released, but not during development time. An IV detector is an approach that can automatically detect an IV smell at the development time before the application is released. An IV detector is implemented as a plugin and it's compatible with the Android Studio to be easily used by the Android developer. In the future work, we are plan to automatically first to mix between static and dynamic analysis, and then to automatically fix these NIV smells using code refactoring. Thank you.